So, lesson 1, a force is a push or a pull. That's as good a definition as anything for now, I guess. It's a vector. That's really important, so we're going to actually choose to underline that, because this is the unit where suddenly stuff is going to be moving left and right and up and down and at an angle, slanty. And it has a magnitude measured in units of newtons. The units for force is newtons, named after a scientist whose last name was? Newton. Very good. Forces are based on interactions between two objects. Some important forces that we study in this course will include the following, and I think I can go like this, and like this, and like this. I think I can fit that all. Yeah, I can. This is not the only forces that we'll be looking at this unit, but these are the ones that you looked at last year. This year we'll look at other ones. We'll be adding electrostatic force, we'll be adding magnetic force, we'll be adding centripetal force, but for now. What did we call the force that was the Earth pulling on all objects downwards towards the planet's center? Gravity. Symbol, capital F, lowercase g. Gravity. What did we call the force that was the microscopic hills and valleys between an object and a surface that interlocked and prevented or impeded sliding? Friction. Symbol, FF or FFR. I don't know why I had the R there, I just do. What did we call the force that was a surface pushing back up on an object? And it was also the apparent weight of an object. Remember what we called this one?
Normal force.
Normal force. Josh, don't write this next bit down. Some textbooks will use that for normal force. The problem is that looks like newtons and north, and so I find that confusing. So I use this. F with a little subscripted N for normal force. Normal force always points out 90 degrees from the surface. A number of years ago, I was marking provincial exams, and there was a question on the provincial, and the question went like this. Find Fn, the normal force. And a student wrote, it was funny. They still got a 0, but it was at least, you smiled. Okay. What do we call the force from a stretched string, constant throughout the string? Tension. Some books will use a capital letter T for tension. I prefer to stick with my F for a force and a little subscripted T for tension. This next one was kind of a weird one. This was the contact force from an external agent, usually a person. This is when I wanted to have a force from the outside world, but I didn't want to have to write or explain a big story as to where that force came from. What did I call an external outside force? Do you remember? It's the applied force. So in your diagrams, I didn't want to have to tell you, oh, somebody's pushing, or a dog is pulling it, or a horse is pulling. It's applied force. As a matter of fact, when we look at electrostatic force, when we're looking at the forces on atoms, you can't really push an atom. You're going to hear me say frequently, Megan, just pretend it's little invisible angels that are pushing it. Because for all intents and purposes, that works. Something's pushing it. Who cares what? Something is. It's the applied force. What was the force of resistance from the air that was opposite to the direction of motion? And we called this air resistance, but there is a fancy name for it. It begins with the letter D. Does anybody know? Yep. Drag. Problem. Drag is very complicated. Air resistance is very complicated. It's a changing force. The faster you fall, the bigger it gets. The slower you fall, the smaller it gets. It also, Terry, depends on your surface area. The wider you are, the more your drag, the more tucked in you are, the smaller your drag. You really need calculus to do drag properly. It involves drag coefficients and all sorts of stuff. What I'm going to do, I'm going to call it F air. I'm going to treat it mathematically like friction. Really what I'm going to be doing anytime I say find the air resistance force, Alicia, we're going to be finding the air resistance force right at that moment in time, right then, because air resistance is changing. You need calculus. Now, what did we call, it wasn't a force, but it was the vector sum or the resultant of all of the forces acting on the object. What do we call it when we added up all the forces, being the letter N? The net force, F net. The net force, F net. Now I got to go a bit smaller again. I don't think I can fit this all. Maybe I can fit it at 150 though. Hey, I can. Newton's laws. Sir Isaac Newton. I got to pause here, and I got to go on my little Sir Isaac Newton rant. There's a reason we have so much respect for Sir Isaac Newton. If you asked most scientists who was the best scientist of all time, probably the answer you'd get the most, the greatest scientist ever, Sir Isaac Newton. If you ask most mathematicians who was the greatest mathematician of all time, probably Hannah, you'd get, oh geez, I did it for the first time all year. Gabby, probably you'd get Sir Isaac Newton as your answer. We have so much respect for him because he just revolutionized dozens of branches of science. And he did it in about 2 years when he wasn't much older than you, Jeg. When he was about 19, he was in university in London, and the Black Death, the plague, came to London. And back then, as soon as the plague came to your city, if you had any kind of wealth, and he was reasonably well off, you left the city, you moved out to the country for a couple of years, and you let the disease run its course. You let everyone, all the poor people in the city die, you let their bodies fester, you let the street people come and clean up the bodies, bury the bodies. It took about 2 years for any kind of disease cycle to run its course. So he did that. And while he was on the farm, while he was wandering around, while he was just kind of wandering around the fields, aimlessly, not sure where he was going, he thought. He thought, and he thought, and he thought. And in that 2-year span, you can make an argument that no one has ever thought or discovered or revolutionized as much in 2 years as him. During that 2 years, Megan, he invented the calculus. We put a "the" in front of it to make it sound really, really impressive. During that 2 years, he came up with the law of universal gravitation, the one that you saw last year, F equals big G, big M, little m over R squared. And among many, 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 many other things, he came up with Newton's 3 laws of motion. And this was a gutsy move. Up until then, the best, the brightest, the biggest, the most influential scientist had been Aristotle, who was a Greek scientist, Jaron, who lived about 2,500 years ago. Aristotle dominated science for the next 2,500 years. Aristotle was what Newton was taught in university. And Aristotle wanted to explain something very simple. He wanted to explain what happens when you roll a ball. Like this. Here's a tennis ball. Where did I put them? If you take a tennis ball and you roll it on level ground, now my floor is not terribly level, so this may or may not work, but if you roll it on level ground like this, what happens to the ball eventually? It comes to a stop. And so Aristotle wanted to explain this, and here is what he said. He said that all around us in the earth, there is an energy field, a life energy field. And yes, George Lucas had read Aristotle, and he borrowed the idea for the Force in Star Wars. Life energy, he called it. You get life energy. You get it by eating plants, And animals. Where do the animals get their life energy? From the plants. Where does all life energy come from? Where do plants come from? The earth. The earth. He wasn't thinking about the sun. He said, you know what? All life energy comes from the earth, and it wants to return to the earth. Where do we put you when you die? In the earth. What happens to your body? It turns back into the earth. Oh, this is a pretty good argument so far. Explains a lot. And he said, when you roll the ball, what you're doing is you're sharing some of your life energy with it. But since it's on the ground, the earth is bleeding the life energy off of it back into the earth, and that's why it comes to a stop. It's not a bad explanation. And it was his explanation for why this happens. This has life energy. Where does the life energy want to return to? The earth. See? See? Garbage. Completely wrong. But not a bad explanation. Satisfies some stuff. And they branched out into all sorts of, they really took it, this is where the whole earth, wind, and fire and all that stuff, you may have heard those terms, comes from. Wrong. Completely wrong. Except it was taught for 2,500 years and it explained an awful lot. And then here came this 21-year-old punk kid who said, "Pia, garbage." Yeah, I know you guys have believed it for 2,500 years. I know Aristotle, we call it Aristotelian physics or Aristotelian science. I mean, hey, even George Lucas still embraced part of it for his movies. No! Newton said this. I can describe all of motion in 3 rules. In fact, in 2 laws and 1 3-variable equation. The first law, Newton's first law. Now, it usually is stated as follows. Objects at rest tend to remain at rest. Objects in motion tend to remain at motion. That confuses the heck out of me, so I never even write that. Newton's first law, I wrote it this way, and even this is a terrible way to write it. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Basically, here's what it says. The only way that you can accelerate an object or change its velocity is to apply an unbalanced outside force. So let's look at Ben right now. Are there forces acting on Ben right now? Yes! What's the obvious one, Ben? Gravity. Are you accelerating downwards? No. Then there must be a force exactly the same size as gravity, no bigger, no smaller, in the opposite direction of gravity also acting on you. That's what Newton's first law says. Because if that was not true, he would have to be accelerating downwards, sinking into the ground like quicksand, or accelerating upwards, taking off like he had a jetpack. The fact that he isn't means the net force is 0. That's Newton's first. If you're not accelerating, the net force is 0. Now, does that mean he can't be moving? No. If he was moving at a constant speed without accelerating, your net force is 0. You see what Newton just did, Sydney? 500 years ago, before hot air balloons had even really been invented, he was visualizing outer space. It's pretty impressive. He was imagining what it was like past the Earth. Got to realize, this was only about 80 years after Galileo and Copernicus said, hey, the Earth goes around the sun. And he was already then saying, well, if the Earth goes around the sun, hey, what's past the Earth? What's out there? So his explanation, Jake, for the ball rolling, is it slowing down? Is it accelerating? Yes. Then there must be a force acting on it. There has to be an unbalanced force acting on it. That's why it came to a stop. What is the unbalanced force acting on it? Yeah.
Friction.
Actually, if I was sliding something, friction, when an object rolls, actually there's very, very little friction. What's stopping it is mostly air resistance. If I had a bowling ball, I need to buy one of these days, and I rolled it on a level floor, the bowling ball will continue to roll for an awfully long time because the friction between the bowling ball and the ground near 0. It's only air resistance, and since a bowling ball has so much mass, air resistance isn't doing much damage to it. That's why bowling alleys, bowling balls roll so well. Even if you don't give it a good push, you get a gentle push, it'll keep rolling for quite a while because those bowling lanes are pretty level. This is often called the law of inertia because it also says this. Objects possess inertia. What's inertia? Inertia is sort of like mass. It's related to how much mass you have. The more mass you have, the more inertia you have, the more resistant you are to a change in acceleration, to a force. We have Calvin and Hobbes. It says, explain Newton's first law of motion in your own words. Calvin looks all puzzled. And then he has his breakthrough. He says, oh, Yakafub ma grug pabawump zinc watum gazork chumble spuzz. Here, he just explained Newton's first law in his own words. He says, I love loopholes. Don't try that on a test. I won't give you marks. Newton's first law. Objects at rest tend to remain at rest. Objects in motion tend to remain at motion. That's a terrible way to say it. Newton's first law. If you're accelerating, there's an unbalanced force. If you're not accelerating, net force is zero. That's really how I remember it. So, how would this look in the real world? Now, I got to pause my video, I suspect, here. Newton's second law. Back to our notes. Newton's second law is the mathematical relationship that allows us to calculate the force on an object. And you guys all memorized this one last year. F equals what times what? You'll notice I drew the vector above the F and the A because the direction of the acceleration is the direction of the force. Then I wrote, we'll explore this more later. We'll be spending the next 3 weeks looking at variations of this. Actually, Newton wasn't interested in force. He actually wrote the A by itself. He wrote it as A equals F over m. He was much more interested in acceleration, but we've gone to this one. Newton's third law. This is often called the law of action-reaction, and it's usually said something like, for every action there is an equal and opposite reaction. What? I find that terribly confusing. I think of Newton's third law as follows. Forces come in pairs. You cannot have a force by itself. Now, Alicia, you can have a force by itself in a free body diagram if you're only drawing one object in the free body diagram and all you're looking at are the forces on that object. But I'm telling you, you cannot have a force by itself. Forces come in pairs. Or, as an equation, the force of object A on object B is equal to the force of object B on object A, but negative in the opposite direction. Forces come in pairs. Okay? So let me show you a couple of examples. Can I borrow Sydney and Dorothy, please? Can I borrow you two quickly? And I'm going to leave the video recording during this, and I'm going to put it, Sebastian, if you don't mind, right here, just so it can hear my explanation, even though nobody can see what's going on. We'll see if it picks up my voice. Can you stand right there, Dorothy, for me? And Sydney right here, facing each other. And put your hands on here, put your hands on here. Now, Sydney, both hands. This is a scale. The black is kilograms, and if you multiply it by 10, that's roughly newtons. I'd like to see how big a force you guys can exert between you guys. Push hard, push hard, push hard, push. What? 15 times 10, so about 150 newtons? Okay. Who thinks they can do better? Jake, come on up here. Sydney, sit down. Dorothy, stay here.
I think it's
Terry. Terry? Okay, Terry, come on up here. Okay. Ready? Push. Go. Now, what's the problem here?
I need larger force.
The problem is, I just told you that forces come in pairs. And because Dorothy can't exert a force bigger than 150 newtons, that means Terry can't exert a force bigger than 150 newtons. If he tries, what happens? The whole system started to accelerate. We had an unbalanced force. Okay? But it has nothing to do with how strong Terry is. In fact, if I hung a feather from a piece of string right here, and you pushed with one finger to move the feather, and maybe you were applying a force of like 0.1 newtons, even if you used a baseball bat, you're still applying a force of 0.1 newtons because forces come in pairs. The feather can't exert a force bigger than 0.1 newtons against your finger. It has nothing to do with how hard you push. Okay? Thank you. You can sit down. Terry, you can stay up here. You're a fairly strapping young man. Terry, can you do me a favor? Could you get in push-up position, please? You have any shoulder issues?
No, I'm good.
Okay, good. Push-up position. Could you do a... Can you do a push-up, please? Which way was he pushing with his arms? Do it again. Go down, go down. Stay there, stay there. Okay, push. Which way are you pushing with your arms?
Up or down?
Down. Which way is he accelerating? Up. So it can't be his arms that push him up. Can't be. There's no way you can push down and have your body move up. What's pushing him up? Can you go down again? Just an inch off. Okay, stay there, stay there. Okay, he's exerting a force right now. Push down, accelerate up. What's pushing him up? It's not his arms. I'm telling you right now. You can get up, Terry. What's pushing him up? Okay, let me ask you a different question. Why can't you do push-ups in a swimming pool? You can't. Why is it tougher to do push-ups on a mattress? Because it is. What pushes you up? Ben. The ground. The normal force, as a matter of fact. What you're doing is you're applying a force down on the ground with your arms, and the ground is saying, oh, I'll apply a force back. You know why? Forces come in pairs. And that's what pushes you up. And that's why you can't do push-ups in a swimming pool. No normal force when you're floating. That's why when you're on a mat, I don't know if you've ever done push-ups on a mat. I always cheat. I put my hands outside the mat because it's way tougher to do push-ups on a mat because the mat is flexible. It doesn't want to give me as constant a normal force. It's more awkward. Okay? Push-ups. Bring up my little physics toy. Okay. Little helicopter. Sorry for those of you who are watching this on the internet, but you'll hear my voice. Okay. Which way is the helicopter accelerating? Which way did it accelerate? Up. I'm going to go over Tyler if I can. Tyler, which way are the propellers exerting a force? Can you feel it?
Down.
Down. So then what's accelerating it up? Can't be the propellers because the propellers are pushing downwards. What the heck is making it go up then? Can't be the propellers. There's no way you can push down and accelerate up. Something else must be accelerating it up. What's pushing it up? Jason? Air. Oh, is that why? Would a helicopter work in outer space? No. Would a helicopter work underwater where the air is thicker, liquid? Very well. In fact, we call that a propeller. It's how boat motors work. That's why propellers work so well underwater. Boat motors work really well underwater. But the boat motor does not push the boat forward. The propeller pushes backwards. What pushes the boat forwards? The water does. You really want to start thinking about how forces work and which way you're exerting a force to do something basic. Even so simple as, Megan, can you come stand right here for me, please? Even so simple as walking. So I'd like you to stand here, and I'd like you to face that way and take 3 or 4 quick steps like you're power walking. Now, which way was Megan accelerating? That way. Megan, which way were you exerting a force? Think about it. Come back here and do it again. Which way are you exerting a force? I'll give you a hint. Go back here. Okay. If I told you to run in those shoes, might your foot slip when you started off?
Yeah.
So which way are you pushing that would make it slip that way?
That.
Ah! Which way when you're walking are you pushing? Backwards. But which way are you accelerating? Forward. So it's not your feet that make you go forwards. Right? Question is, which force makes you go forwards? Ben, what? Is that why it's tough to walk on ice? Oh, thanks, Megan. You can sit down. In fact, on ice, where there's little or no friction, especially wet ice where there is almost no friction, you don't walk. How do you walk on ice? What you actually do, watch me and you'll recognize the motion, you go into a controlled free fall. You lean forward just enough so that you start to fall forward, and you shuffle your feet underneath your body to keep your center of mass above your feet. That's how you walk on ice. Totally different way of walking. You fall, controlled. Why? No friction. Okay. Newton's third law. Start thinking about the way you move. Hey, which way do your bike tires push? I'm telling you, your bike tires don't push forwards. Which way do your bike tires push? Backwards. So what pushes you forwards? Friction. That's why it's tough to ride on snow. That's why it's tough to bike on ice. Newton's third law. By the way, if we're talking about Olympics, why would an athlete want low mass shoes, I wrote here? So Usain Bolt, why would he want lightweight shoes? Why wouldn't he want heavy shoes? And can you give me an explanation that uses some good physics? What's Newton's second law? I agree with you. So you know what? It says this. Right? Let's assume at the Olympic level, Gabby, you've done enough training, you've done enough weightlifting so that you've maxed out your force. You cannot possibly exert any more force. You've developed the muscles in your lower body such that they can't get any bigger or stronger. So you're stuck with the force. If I'm stuck with this value, how can I get this value bigger? Take this number, make it smaller, right? In fact, you know what? If I wanted to do an explanation, I would probably do something like this. So I'm stuck with a force, but if I have a tiny m, I can get a really big acceleration. Or if I have a really big mass, a very small acceleration. That's why over the past 20 years, sporting equipment, well, has sporting equipment gotten heavier or has it gotten lighter? Pretty consistently, except there's odd exceptions where you do want more mass, but for the most part, lighter. Okay. Pardon me? Oh yeah. Oh yeah. Well, what's the difference? The 100 meters is the classic. What's the difference between first and eighth? About 0.3 of a second. Yeah, you know what? The weight of your shoelaces might make a difference at that point. In fact, I'd be willing to bet that all of those shoes don't have shoelaces because that would also create air resistance. The bow would be terrible air resistance. Really? Well, hey, for those 16 or 20 strides that they do for that long, probably. They have it down to a literal science. The two big events that physics changed, high jumping. So you guys have seen how people high jump. How did they used to high jump? Scissor kick or dive forwards over it. And then a high jumper who also had a physics background named Dick Fosbury. It's called the Fosbury flop. A physicist and him worked out that if you went backwards over the bar, you could actually rotate your center of mass around the bar. When the high jumpers go over the bar, they don't in terms of physics. Their center of mass actually goes below the bar. And they rotate their body around their center of mass. That's why they do that arc kick and if you do it just right, now it's tough to master, but if you get the hang of the timing, oh, now Jaron, you're jumping under the bar to go over the bar. Suddenly he won a gold medal and everyone went, oh, that was one big one. About 12 years ago, swimming changed dramatically in the backstroke. It wasn't Mark Tewksbury. Oh, what was the guy's name? A guy who was a lousy backstroker suddenly began setting world records because he had talked to a physicist who had told him, you know what? Dolphin kicking underwater is way more efficient than swimming over the water. And so he started doing nothing but sit-ups. He didn't practice sitting. He did crunches, more crunches. And he practiced being able to hold his breath for a long time. And so his backstroke, what he would do is he would jump into the water and he would dolphin kick the first 2/3 of the pool and then pop up yards ahead of everybody else and then start doing a pretty bad backstroke and everybody would slowly catch up. But then he would hit the turn, dolphin kick again. Now it's tough because he's not breathing as much as everybody else, so you really need some good stamina, and he would get slower and slower and slower. But if he did it right, he'd still win by about a meter or two. So then swimming outlawed it. Now, if you watch the Olympics, there's that rope about 15 or 20 meters in. That's when they have to stop dolphin kicking by. So they look up, and as soon as they see their head about to get to that rope, they know, I better come back to the surface. Okay. Oh yeah, lots of physics in sports. Huge amount of physics in sports, especially in the U.S., where they really got the infrastructure and the money. A force with which you have had some experience is the force of gravity between you and the Earth. This force is also known as weight, and it's measured in newtons. We do this wrong in English. When I say to Jake, what do you weigh? And you tell me kilograms, that's wrong. You should really say newtons. And it's mg, it's your mass in kilograms times 9.8. We're sloppy in English. Pounds is correct. In the old system, pounds was a measure of force. So that scale that I held up for Sydney, it had pounds and kilograms. It actually has a force, pounds, and a mass, kilograms. It's kind of a weird scale. It's how they're all set up. Force of gravity is not the same thing as mass, although they are related. Mass is the amount of matter in an object, measured in kilograms, or slugs under the old system. To relate mass to force, we need to know the number of newtons of force per kilogram of matter. This quantity is known as the gravitational field strength. And the gravitational field strength here on the Earth is 9.8. Hey, where have you seen that number before? 9.8. I've seen that somewhere. Okay, we called it the acceleration due to gravity. Ben, another term for it is that's also the gravitational field strength. If you're accelerating at 9.8 meters per second squared downward, what that also means is that the Earth is tugging down with 9.8 newtons on every kilogram of mass. 9.8 newtons per kilogram. Oh, and it gets smaller the further you get from the Earth. Outer space. The moon's gravitational field is about 1.6 newtons per kilogram. What that also means, Dorothy, is if you dropped an object on the moon, it would accelerate at 1.6 meters per second squared downwards. So for gravity, we said this. Fg equals mg. Direction down. Usually with gravity, it's so obvious that it's down, we often get a bit sloppy and forget the direction. The G tells me, you're heading downwards, things don't fall up. By the way, they're trying. So many particles come in pairs. Protons have their opposite electrons. They've often wondered if the graviton particle has its opposite anti-graviton. They're looking. Find the weight of a 10 kilogram object. Did it say find the mass of a 10 kilogram object? It said find the weight. What's the weight? The weight is the gravitational force, which is given by mg, which is given by mg, which is going to be a mass of 10, On the Earth, what's the gravitational field strength? There's your new term for the day, 9.8. Don't reach for your calculator. It's your 10 times table, for Pete's sakes. On the moon, what's the gravitational field strength? What did I say in the little above paragraph? 1.6. So a 10 kilogram mass on the Earth has a weight of 98 newtons. That same mass on the moon has a weight of 16 newtons. So let's suppose that we're in the space shuttle. We're in the crew cabin, the cargo hold of the space shuttle. We've pressurized it. There's air. And Jason and Terry are astronauts. Okay? And Jason is on one end floating in the cargo bay. And Terry is on the other end floating in the cargo bay. And Jason takes a bowling ball and he gives it a push towards Terry, so the bowling ball starts to drift across the cargo bay. And Terry decides he's going to stop the bowling ball with his face. Will it hurt? Or to ask the same question another way, let's suppose Terry is floating in the cargo bay and he has a hammer and he needs to hammer a nail. Can he hammer a nail in outer space if he's floating, if he's weightless? In other words, if a mass hits another mass, will it apply a force? Will it hurt? Let's see if we can reason this one out. So, Terry, could you stand up? Could you extend your chin like you're about to be hit in the face by a bowling ball? Okay? So here comes the bowling ball. A little smaller. And we're going to get right to here. We're going to freeze frame for a split second. Okay? Does it have a velocity right now? Yeah. Okay, it hits Terry's chin. What's its final velocity going to be? 0. So here's my first question. Did it accelerate? Was there a change in velocity? Yeah. Did it have a mass? So if there was an acceleration and a mass, did it apply a force? Oh, we were able to reason that out with physics 11, actually. Can you hammer in outer space? Does the hammer have a mass? Yes. Will its final velocity be 0 after it hits the nail? Yes. Will its initial velocity not be 0? Yes. So will there be an acceleration? Yeah. Well, yeah, you can hammer in outer space. It would hurt. Now, in outer space, the advantage you have is if it's a really heavy box, I can just get it going and then let go, and it'll drift the rest of the way, and you'll have to bring it to a stop and apply a force to bring it to a stop. So it is easier in some ways to move stuff around in outer space. But don't think that getting hit by a baseball bat in outer space wouldn't hurt. It would. Example 3 says, select the best answer. Okay? Yeah, you have to turn the page.
It wouldn't hurt as much, though.
It would hurt exactly the same amount. Exactly the same amount. If I punched you in outer space, you and I could have a fist fight in outer space, and it would hurt just as much as here. Now, the only issue is, stand up. I'm going to punch you, but not really. Okay? For me to punch you, which way do I exert a force? Don't say forwards, because I don't. For me to punch you, I push with my feet backwards in order to torque my shoulder forwards in order to give you an impact right there. That part I couldn't do in outer space. I would purely be punching you with nothing but upper body strength. So in that way, it wouldn't hurt as much. Your technique wouldn't be as good. Okay? Example 3 says, select the best answer. If the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D may remain at rest, move at a constant, or all of the above. Once again, we're going to vote. Once again, how high you hold your hand is how sure you are of the vote. Once again, if you don't vote at all, I'll lovingly make fun of you. Okay? You ready? So if the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. Who says A? No one. Who says B? No one. Who says C? 1, 2, 3, 4. Who says D? Lots. Who didn't bother voting? Who didn't bother voting? Are you ready? You have to pick A, B, C, or D. Next time I want you following along a little bit, okay? I know you're still learning the language, and so I shouldn't pick on you too much, Victoria. But gotta vote. Okay, here's the options, folks. You can convince me that you're right or that someone else is wrong. John.
Depends on the situation.
Okay, give me the situations. And you know what? Let's use this. Show me how A could be correct.
If it's on the ground, it would remain at rest.
How about not even on the ground, I dare to say. As long as there's a surface below it that can apply a normal force in the opposite direction. I agree. So A could be right. What about C? That's a pretty easy one to visualize. Just drop it. So since A and C are both right, I'm leaning towards D. How could B be right?
Doesn't specify which way the velocity is going. Couldn't the velocity be horizontal?
That's a possibility, but there's a two-word answer that would work.
Terminal velocity.
Terminal velocity. When I jumped out of an airplane, I mentioned that I jumped out of an airplane. When I jumped out of an airplane, eventually I stopped accelerating. Why? Because air resistance canceled out gravity down. Didn't mean I was hanging in midair, not moving. Terminal velocity at that speed was fatal. Oh, but then I changed it. I increased my cross-sectional area. We call that a parachute. And I hit a new terminal velocity. I did. A survivable one. I'm not a very terminal velocity. No pun intended, or pun intended. So yeah. D. Here's how I would answer it. A, sure, on the ground. B, terminal velocity. And C, free fall. Technically free fall in a vacuum, or ignoring air resistance. Technically free fall with a bowling ball that's pretty aerodynamic and has enough mass that air resistance really isn't going to be doing much anyway. But even a bowling ball would eventually hit terminal velocity. Pretty high terminal velocity, but it would hit it. So Newton's second law says that if we have balance, oh, this is a typo and I've been meaning to fix it for years. First law says that if we have balanced forces, an object at rest remain at rest, and objects in motion remain at motion. If we have unbalanced forces, then the object accelerates in the direction of the net force. Newton's first law really says, Jaron, if you're not accelerating, your net force is 0. If you are accelerating, your net force ain't 0. It also works backwards, by the way. If your net force isn't 0, you are accelerating. If your net force is 0, you're not accelerating. As an equation, as a summary, we often write this. The net force equals ma. This symbol here is the sum of all of the forces. So if you add up all the forces, Jason, vectorially, which means direction is going to play a role, that equals ma. We're going to go right to the tone, but we're not going to finish the lesson. We'll finish off the lesson next class. Note, I wrote, these units are the same. Newtons per kilogram is the same as meters per second squared. You may have suspected that when I told you that the Earth's gravitational field was 9.8 newtons per kilogram, and you've been saying all last year that it was also 9.8 meters per second squared. You might have suspected that the units are the same. I'm going to convince you. Newtons is a measure of force. Force is what times what? Dorothy, you're right. You're right. So are you saying that newtons is actually kilogram meters per second squared? Can you see the mass times acceleration hidden in there? See it? Kilograms and then meters per second squared. So what would newtons per kilogram be? Newtons per kilogram would be kilogram meters per second squared. Oh, but you're dividing by an extra kilogram. That's what newtons per kilogram means. Oh, and Sebastian, what happens to the kilograms is, and what's left behind? They are the same. So another term for acceleration due to gravity is gravitational field strength. Measured in newtons per kilogram. I'm not going to be fussy whether you write 9.8 meters per second squared or 9.8 newtons per kilogram. For what it's worth, if you're talking about an acceleration, like last unit, it's proper to use meters per second squared. If you're talking about a force like this unit, a gravitational force, it's proper to use newtons per kilogram. I don't care, Dorothy. I'll try and do it properly, but I'm not going to take marks off. Turn the page. Example 4 says, find the unbalanced or the net or the resultant force in each case, including the direction. All right. You know what? How about let's call this north, east, south, west, so we have some kind of frame of reference. What's the net force in A? Magnitude and direction. 2 newtons. Direction? 2 newtons east. What's the net force in B? Magnitude and direction. 3.7 newtons south, I agree. Hey, what's the net force in C, magnitude and direction? Now we got to do some vectorial math here. 1 Newton north, I agree. What's the net force in picture D? Eight to the right, 3 to the left, means 5 to the right or east. What's the net force in picture E? You know what? We got to do north-south first, and then we got to do east-west. Jaron, what's the north-south net force? Okay, 4? I don't think so.
0.
Why? Because we got to do vector math. I agree. So we can ignore that. What's my left, right, east, west force? Magnitude and direction.
75.
Yep. Nice. F. Okay. Algebraically, if you know that y is bigger than x, what would the algebraic expression be for your net force here? Y minus x newtons. Direction? South. South. We're going to pause here.